Hi everybody. So now that we've introduced the concept of rotational kinematics, the idea of how fast something's spinning up or spinning down as the case may be, let's try to tie it back to the translational kinematics that we've talked about previously. Think about it. What is necessary for there to be an acceleration? What is the definition of an acceleration? Well, it's a change in velocity with respect to time, dv dt. Well, the velocity has two components to it. It has a magnitude and it has a direction. Up to this point, we've mostly just simply been concerned with the changes in the magnitude. Did the robot speed up or did the robot slow down? However, now that we've introduced the idea of rotation, it also turns a corner. And so it is possible for the robot to maintain a constant speed. Its magnitude of its velocity stays the same, but it changes its direction. Well, that's still a change in velocity, so that's still going to be a change in acceleration. And so for the next couple of lectures, we'll be talking about what happens with that. So the first thing we have to do to understand that is the concept of tangential motion. And don't be confused by that. Tangential motion just means the motion along the track. So as the robot is maybe driving around in a circle at a constant speed, that constant speed would be its tangential motion. So today we're going to derive those equations that we need to translate between a rotational motion and then this idea of a tangential motion, which is kind of my along track motion. Let's get started. Okay, so when we're thinking about tangential motion, one of the easiest ways to kind of introduce the concept is to think about that transition between something rotating and then something translating, something moving in a straight line through space. And one of the easiest things to think about is if I have a ball on a string and I'm whirling it around over my head. This was classically called a sling. You took a piece of fabric and then you folded it in half and you put a stone inside the end of that fabric, so it was kind of tucked inside. You rolled it over your head. Now you held it so that you had one piece of fabric, one end of the fold between these fingers and the other between these fingers. So you whirl that to quite some speed, and then you release the top fingers, which makes the cloth straighten out, and that ball goes off in a very straight path. So let's think about that. If I have this case of this ball just on a string and I'm whirling it around, and I just let go of the string. I'm not going to throw it. I'm not going to do anything. I'm just going to whirl it straight over my head and let go. What's going to happen to the ball? Pause the video, think about it, and let's write down some answers. Well, if you look at the diagram here that we've got, then the string is rotating this way, so the ball is also going this way. But what's happening is the ball wants to go straight. The ball wants to go directly in this direction. However, this string is pulling on it and it's applying a force in this direction. And so that means that its angle, its orientation to my I and J components here is going to be continually changing, because even when I'm up here, there's still a force pulling me towards the center. And we're going to deal with this in more detail next time. So the end result then is that it's going to move in this circle just like this. However, the instant that I stop having that force, the instant that I get rid of that string there, well, now there's nothing to make it keep going in a curved path. There's nothing to keep changing its velocity. Well, you know, by Newton's second law, if there is no external force, then there can't be any change in velocity. So that means then that my ball is going to have to just keep on going straight forever, hopefully forever, straight on as far as it can go, right? It's become a projectile. So if we think about this in terms of Newton's laws, it starts to make a little more sense. So I know that the sum of the forces on the ball must equal, let's say, dp dt, but if the ball's mass is constant, then we know that that's also the acceleration, right? Well, as long as I have this string here, there is a force being applied, so there must be an acceleration. That acceleration is not changing the speed, but it is changing the direction. But as soon as I get rid of that string, as soon as I let go of it, then now the sum of my forces is just equal to 0. And so then that tells me that the acceleration must equal 0, which means that my velocity can't change, and so I'm just going to continue on out in this straight line. That's the essence of tangential motion. And don't be confused by this idea of tangential motion. We call it that simply because this along track velocity, this velocity as I go around the loop, is always going to be at a tangent to my path, to my circle that I've got in here. So it doesn't matter where I am on the circle. So you see that even right here, as we've shown, it's only going to touch the circle in one place. But even up here, it's only going to touch the circle in one place, and here. So my speed is unchanged, but my velocity is changing. But that velocity is always going to be tangent to its rotational path. And it doesn't even have to be a circle. In fact, if I have an orbit, let's say I've got the sun here, and I've got a comet or something that's coming in this way, right? Its velocity will also always be tangent to its path coming along. So the idea is the same no matter what kind of path that it's taking, what kind of curved path that it's taking. It's still going to be tangent to it. Okay, so we now see that I've got some sort of a tangential velocity, which is just the along track velocity. If you were driving in your car around that circle, that's what your speedometer would show. If you're driving at 50 miles an hour around this track, say you're on a test track or something like that, then your speedometer is just going to show 50 miles an hour. Your direction is continually changing, but that 50 miles an hour is your tangential velocity. All right, so let's see if we can work out an equation that relates the tangential velocity to the angular velocity. We're going to do this the same way we always do. Think about what physical quantities could change and then decide, are they directly proportional or are they inversely proportional? If they're directly proportional, they go in the top. If they're inversely proportional, they're going to go under a fraction bar. All right, so the first question says, which of these scenarios would have a faster tangential velocity? Now this might be a little tricky, but think about it. Make your first guess, commit to it, and then we'll go from there. So we're thinking about two cases, and let me just draw them here. So in one case, I've got a small circle here, and then in this case, I've got a big circle here. Let's see if we can put our center actually in the center, like this. Now, let's remember, when we're doing this, we always want to keep everything the same and change just one thing. So in this case, we're going to have these moving at the same angular velocity. So they're moving at the same angular velocity. So that means that the rock or stone or ball or whatever I have here, when it reaches here, this one also has to reach over here. When this stone reaches here, this one also has to reach here. When it reaches back all the way to the beginning, this one hits at exactly the same time. If that were not true, they wouldn't have the same angular velocity. Remember, angular velocity is the number of revolutions per second, for example, or radians per second, degrees per second. So if they have to make that path in the same amount of time, which one has to travel further? The small radius or the large radius? Well, the large radius is going to have to travel further, isn't it? And you can see that. So if it has to travel a greater distance, a greater circumference, if you want to think of it that way, in the same amount of time, it must be faster. Its speed, its tangential velocity must be faster. And so that tells us that it must be the large radius. Right? Stop and think about that. Make sure that makes sense to you. If I've got a larger path, but they've got to make that orbit in the same amount of time, well, then this guy better be trucking because he's got a lot further he's got to go. All right, so now let's suppose I have, so I've got this larger radius is going to have a faster tangential velocity. For that, let's draw our second idea here. So which scenario here would have a faster tangential velocity? So here we've got the same radius. So the string is the same. So this is R and this is R. And we're trying to make those the same, but it's going to be close enough. Let's get rid of some of our extras here and try that again. All right, we will pretend that that's the same radius. Okay, so they're the same distance, so they've got to travel the same amount of time, the same amount of distance around the track. However, this one is going to have a very large angular velocity, whereas this one, say, is going to have a small angular velocity. So the angular velocity of 1 is greater than the angular velocity of 2. So for which one is that speed, that tangential velocity here, going to be faster? Are they making it all around the circle at the same time? No. Which one's going to get there first? Which one's going to complete this orbit first? Well, that's going to be this guy, right? And so if he is moving around the track faster than this guy is, well, then my tangential velocity must be higher if I have a large angular velocity, a large omega. All right, so those are the only two variables that we have to work with. So we know that our relationship between the tangential velocity must depend upon the radius of my orbit, my circle, and it also must be determined by how fast I'm spinning. Both of those hopefully make sense now. All right, so the next thing we have to decide is whether they are directly proportional or whether they are inversely proportional. So let's think about the radius of rotation. So if I've got a larger radius, we know that that has a larger tangential velocity. So are they directly proportional or are they inversely proportional? Well, since as the radius goes up, the tangential velocity goes up, they must be directly proportional. Okay. And now how about the angular velocity, omega? Well, we decided that if I have a higher angular velocity, then I'm also going to get a higher tangential velocity. So those are also directly proportional. All right, so now what I want you to do is, given that, I want you to pause the video and I want you to come up with a mathematical expression that relates the tangential velocity, this VT, this along track velocity, to the radius and to the angular velocity. Pause the video, do that now. Have you got it? This is an important technique, and it's one that we've been doing all semester, and it's one that you're going to do for the rest of your career. Anytime you're trying to analyze a situation to figure out what's going on, you're always going to look at the physical properties that are changing, and then you're going to say, okay, is this one directly proportional or inversely proportional? So I can tell how it's going to vary. Well, in this case, I'll write it out here. Well, we'll put it here. We can still see it. So my tangential velocity then must equal omega times r. They both have to be in that direction. Okay. Now notice that I have written this as a scalar magnitude here. So technically it's a speed, right? And we have to do that because if you think about it, what is the direction of my omega? In the way that I've drawn it here. You might say, oh, well, it's counterclockwise. Well, it's clockwise when you're looking below. So you remember from last time, I used that right-hand rule. And so in this case, it's coming out, it's going in the same direction as my thumb, so we would say that that was positive. However, does it really make sense to have that tangential velocity be in the same positive direction as omega? Certainly it's not, right? It's not coming out of the page if I think about trying to draw this in 3 dimensions. So I'm going this way, so I'm going counterclockwise. Here's my axis. And so omega is actually in that direction, but VT is actually in this direction, and in fact it changes its direction because that's what makes it a tangential velocity from there. So I can't talk about equating vectors here. All I can do is equate the magnitudes, the scalar magnitudes from this. That's still very, very useful. All right, so this kind of idea basically sets the stage for all the other relationships that we want to look at. So if I want to know my speed, then all I have to know is, okay, how fast am I going and what is my radius? Let's take a look on the next page. Okay, so we know we also have to have a constant of proportionality. So for example, let's go ahead and write our equation here again. My tangential velocity is omega times r. There really should be some constant c in front of that. Now, if I choose my units of omega to be radians per second, then the units of that constant is going to be 1. So in that case, then I can have VT as simply just omega r. Now, you may complain that, well, this is radians per second and this is meters. What happened to that radians, right? Well, it turns out you can think of radians as being a throwaway dimension, because all it is telling me how many radii it takes to get around that circumference. Remember that our circumference was 2 pi r from that. And so this 2 pi is literally radians from there. So anytime you have a radian, when you're trying to balance the equation on each side, you can ignore that radians in your balance so that you can make sure that everything works out. And so here you see I have radians per second times meters. Well, that leaves me with meters per second, which is what I want. If I were using any other kind of units for omega, so if I could certainly say omega is degrees per second, or we learned that we can say omega is revolutions per second. And I can absolutely do that. But if I do that, then C has to have some sort of function of pi in it. It has to have something to convert my units back in there, because now they're not going to cancel, because I no longer have radians, which is my only throwaway dimension that I can work with. So as a general rule, you're going to want to convert every angular quantity that you work with into radians. It's going to be easier. So even if I told you, say that something was going at 2000 RPM, well, you remember from what we did last time, that's 2000 revolutions per minute. And so if I want to convert that to radians per second, because I want to be in SI units, then I would have, well, 1 minute is 60 seconds, and then don't have room next to the camera here, but then 1 revolution is 2 pi radians. And so then that will give me my answer in radians per second. And you're always going to want to do that conversion. So just make that a rule. Always convert everything into radians. Just like up to this point, we've converted everything into meters, kilograms, and seconds. Now you're going to convert it into meters, kilograms, seconds, and radians, so that it works out for you. Right? Just keep it as a rule. Do your math, do whatever equations you have to do, and then if it wants it in revolutions per minute or something like that, then convert back out. That will keep you from having to learn a whole bunch of constants that are going to go in front of here. So instead, we can just stay with our equation as it is right now. Okay. Now, as I mentioned, this kind of format here, this equation for the tangential velocity, also applies if I'm trying to find my distance around the track. So, for example, let's draw my picture again that we've got right here. We'll go ahead and give ourselves some space. So let's say that I start here, and we'll call that 0 just for fun, but it could be, you know, my, oops, not omega, it could be my initial theta position, right? So this might be theta 0, but it might be equal to 0 radians. And then let's say that I travel to over here. Well, I have turned through a certain delta theta. And we learned this when we were doing our kinematics equations. So for rotational kinematics, this is the angle that I turn through. And this is equal to theta f minus theta o. If this is 0, if this theta o is 0, well then my change in angle is, my angular displacement is simply going to be theta f. Okay. So now suppose I want to know what is the distance around the track that it traveled. So we call that a path length. It's sometimes called an arc length, because you can see that we're traveling in an arc. But I'm looking at how far I actually moved along the path with that. So think about it and see if you can come up with a relationship. Use this as your model. Think about your units. See if you can come up with a relationship between delta x and delta theta. Okay? We know that there's a relationship, but let's see if we can figure out what that is. And then while you're at it, we know that as I'm rotating around, what if I'm speeding up? Well, now I've got some sort of angular acceleration. Well, that means also then I must be accelerating as I'll go around the track. And here I'm talking about my speed. My tangential speed is getting faster and faster and faster. So not only is it changing direction, so it is also increasing its speed. So my speedometer is showing increasing from 50 miles an hour to 70 miles an hour or something like that as I go around the track. So the things I want to find out here are, what are the relationship between delta x and delta theta And what is the relationship between the tangential acceleration? So the acceleration along the track, remember tangential, that t you can mean along the track, and the angular acceleration. Pause the video, think about it, and actually write it down. Let's see how you do. Have you got it? Well, it turns out it's actually easier than you might think, right? I know that delta x has units of meters, and I know that that radius has to be involved in there, right? Because the longer the radius, let's take another circle here with a bigger radius, and I'm going to go the same angular displacement, so that's still delta theta, but do you see that I've traveled a much further distance? So the greater the radius, the greater the distance, and if I want meters, then this has to be meters, and then that would have to be in radians, because that's my throwaway. So to put it in the same format that I have here, then, my delta x along the track must equal delta theta times r. And again, if I started from theta equals 0, then this theta is simply just whatever angle I ended up at. All right, now hopefully you see the pattern. We can do exactly the same thing for the acceleration. If you think about it, the larger this radius, the more acceleration along the track I'm going to get. So I could write then my tangential acceleration then must be equal to my angular acceleration, how fast my theta is speeding up, times my radius. And let's make sure our units work. So this is meters per second squared. This is radians per second squared. And this is meters. And so you see radians is my throwaway unit, and I get meters per second squared, so it all works. So these are the fundamental mathematical relationships between our along track, our tangential quantities, and my rotational quantities. So these are going to be very important for you to know, and you should make a flipbook for each one of these. All right, so let's take a scenario and let's apply what we've learned. So here, suppose we have a 0.5 kilogram stone, and it's inside a sling that is 1.2 meters long. So that's after it's folded, it's sitting in here, and it's 1.2 meters long. So what's the radius? Well, it's 1.2 meters, right? As I'm swirling it around, it's 1.2 meters. It's going to stay all the way at the end. All right, so we whirl it around our head at a rate of 12.2 radians per second, which, by the way, is very fast. But if you're athletic, and the people in medieval times who were learning to do this, they were very athletic with that. They were very good with that stone, so you could get it going very fast. We want to determine the velocity and the momentum the stone will have when it's released. All right, now if you want to challenge, see if you can do this on your own. Pause the video and let's see if you can work it out. You already know that you're going to use something like this to get your final answer. You also know how to find, once you know the tangential velocity, for example, you can now also find your tangential, your momentum, sorry. As soon as I release it, that tangential velocity becomes my actual velocity, right? Because I'm no longer moving along the track. And that also then gives you your momentum. So give it a try. Pause the video and then see if you can get it. And then let's come back to this and see how we do. All right, you ready? Now, don't just wait for me to do this. The practice is a big part of the learning. You can't learn just by simply watching me talk and watching me write things. Nobody can learn that way. You can only learn by sitting down and thinking about it on your own from that. So it's very important that you're not just watching the video and waiting for me to show you how to do this. Okay, so our scenario then is we want to find the velocity and the momentum, those are both vectors, after the stone is released. All right, so we've launched our stone through our sling at our target. All right, so let's draw ourselves a diagram. Probably the easiest way to do this is to do it overhead because, I can't draw in 3D. So let's say that, this is me, and that's my beak nose looking down on my head there. And I'm whirling it around, we'll say in this direction, with some omega. And the sling length then is r. Okay, and we've said that the radius is 1.2 meters, and we said that omega was equal to 12.2 radians per second. And in the coordinate system I've defined, it's going to be positive. Okay, so our plan then. First of all, we've got to find that tangential velocity. So we will use the tangential velocity equation, definition really, to convert our angular velocity to our tangential velocity. This is equal to the velocity after it's released. All right, so if I release it, let's say I release it right here, which direction is it going to go? Well, it's going to go straight up. All right, so that's also going to be our VT, and I don't know what that is offhand. All right, then I'm going to use our tangential velocity after it's been released. It's now our regular velocity, and we're going to use that to find the momentum. Okay, so that's our plan. Pretty straightforward. Once you write it out as a step 2, hopefully you're like, oh, okay, I see what to do. I see where to go. Let's go to the next page and let's see if we can work it out. All right, so first of all, we're going to need our quantities. And let me redraw my picture up here. So this is going to be R, and we'll say we're throwing it straight forward because I'm aiming at that target right there. And that's going to be my tangential velocity. And then finally, I have a rotational velocity that way. Okay, so our symbols then, we know that R is equal to 1.2 meters. We know that omega, we decided was positive 12.2 radians per second. Let me check my notes, make sure that's right. Yes. And then we don't know what VT is, but we know that it's in meters per second. And we also don't know what the momentum is, but we know that that is going to be in kilogram meters per second. So I have 2 unknowns. I know I'm going to need 2 equations. Our step 2 already gave us what those equations are going to be. So all I need to do then is let's write those down. We said for our first step 2, for our first point of step 2, we said that we were going to use the tangential velocity equation to convert between the angular velocity and the tangential velocity. So let's write that down. So we found that VT, and these are scalar magnitudes at this point. You'll have to assign a direction after we're done here. And so then that's going to be omega times R. Again, scalar magnitudes. Once I have VT then, the magnitude and the direction of P will depend upon the mass of the stone times my tangential velocity once I've figured out what its direction is. So we've got this other symbol, mass of the stone here. Remember that that was 0.5 kilograms. All right, 2 equations and 2 unknowns. We're good to go. I want to establish my coordinate system this way. I'm going to say that this is the I hat direction and this is the J hat direction because I just want my J hat or whatever to align with the direction that my stone is moving. You could absolutely do it in the I hat. You could do it in whatever direction you want. All right, so solving it then, VT equals omega R then is, looking at my notes here, is going to be 12.2 radians per second. Notice it's a scalar magnitude, so there's no concept of positive or negative. And then times 1.2 meters. All right, pick up your calculators. Let's work it out. And so we get 12.2 times 1.2, and that equals, we'll leave a little extra, 14.64 meters per second. Now, I need that velocity, so instead of a speed, so I will say with the velocity symbol, with a vector symbol here, this is going to be in the what? It's going to be in the positive J hat direction. So there's my velocity. And you see now it's actually a vector. But I couldn't decide on that sign in the direction until I actually looked at my picture here and figured it out from there. All right, so my momentum then is the mass of the stone times the tangential velocity vector. And that's going to be just 0.5 kilograms times positive 14.64 meters per second in the J hat direction. And so we multiply by 0.5 and we get 7.32 positive J hat kilogram meters per second. So our momentum is obviously going to be in this j hat direction we've defined as well. So the question is that a lot? You know, sometimes it's hard to get some estimate of, well, okay, is that a lot or is it not, right? So let's compare that to a bullet. So a typical bullet has a mass of around 0.02 kilograms and travels around 300 meters per second. So what I want you to find there is the momentum of the bullet. So find the momentum of the bullet. And that obviously got cut off here, but we want to find the momentum. Wait, how do we do that? Well, we've got this equation right here. It's actually very easy. So I say my momentum is the mass of my bullet this time times the velocity of my bullet. And that is equal to 0.02 kilograms times 300 meters per second. And we'll put it in our calculator anyway, even though you could do that in your head. So 300 times 0.02 is going to simply give me 6.00. And if I'm shooting in the same direction, it's going to be this, kilogram meters per second. So you see that sling bullet, that sling stone, actually has a greater momentum than a modern bullet. And so the damage that can do is extreme. So now maybe you can start to see why it was a capital offense to be caught with a sling. You would be executed, you'd be hung if you were caught with a sling in medieval times. The reason for that is a lot of training and wealth went into producing a knight. You know, he's got his horse, he's got his armor, he's basically immune to all kinds of swords and bashing weapons and all this other sort of thing. But that single sling shot right there could puncture through the armor with no problem whatsoever and take down an armored knight, even if you're just some skinny teenager with that. So these are actually a very, very deadly weapon when it comes down to it. All right. So make sure that makes sense to you, and make sure that you're following what we're doing here. But hopefully that gives you a sense of just how much momentum you can get just by simply whirling something over your head. All right, let's look at another scenario. Take a look on the next page. So here, suppose your robot's wheel is rotating at constant angular velocity, and we want to know how long should we run the motors if we want the robot itself to move 10 centimeters forward. So let's draw that so that we can see what we're talking about here. So we'll just draw the robot wheel here. And I want that robot wheel to travel a total distance of delta x, which we decided was 10 centimeters. I'm going to go ahead and convert that into meters. So that's going to be there's 100 centimeters. That's going to be 0.10 meters. And we actually have 3 significant digits based on this. So 0.100 meters. And I know the radius of my wheel is given to you right here. And so that's 2.0 centimeters. Let's go ahead and put everything into meters, because we know we're going to have to eventually anyway. And so that means if it's 2 centimeters, well, then that's 0.02 meters. And again, we've got 3 significant digits. We should probably go ahead and put those other zeros in there. So 0 meters. And then finally, we know that the wheel is rotating at my omega then is going to be 45.0 revolutions per minute. RPM, remember, means revolutions over minutes. All right, and so what I want to find then is the time required for that to happen. So we're using time. We've got a constant velocity here. I should be able to use my rotational kinematics. But first of all, I've got to convert this delta x into how many rotations do I need to make. So let's think about that in our step 2. So first of all, I want to know how many rotations are in 0.10 meters, because what I'm going to get from my rotational kinematics is I'm going to use this, and I'm going to use my delta theta in radians to figure out what that time is. So just to give me my plan here, I'm going to convert delta x to delta theta using my tangential equation. So this is the one that relates delta x to theta. And then I'm going to use rotational kinematics to find t. So that's my plan. It's 2 easy steps. Working out in your mind, okay, what do I need to do to get there, right? And you probably wouldn't come straight to these 2 steps. But if you kind of think about mentally and maybe on some scratch paper, what are you going to do? How are you going to get there? And then summarize it in step 2, you're going to find that the problem is much, much easier to solve. All right, so we need our quantities and our symbols. We know that omega is going to be 45.0 revolutions per minute, but we need that in what units for rotational kinematics? We need it in radians per second. So let's go ahead and do our conversion. So this is minutes because I want that to cancel. This is going to be seconds here. In 1 minute, there are 60 seconds. And this way you can keep up with it. You know that there are not 60 minutes in 1 second. So we don't have to worry about multiplying, dividing, anything like that. So that's going to get rid of my minutes. I need to get rid of my revolutions, and I want that in radians. And we know that there are 2 pi revolutions, or radians, in 1 revolution. So let's go ahead and do that conversion. So 45 divided by 60 times 2 times 3.14159, and I get 4.71 radians per second. Make sure that you're getting the same thing. All right, the other symbols that we know that our delta x is 0.100 meters. We know that our radius is 0.0200 meters, and I don't know the time. And I also have figured out, based on my step 2, that I'm going to need to find that angular displacement, that delta theta. So I've got 2 unknowns. I'm going to need 2 equations. All right. So let's go ahead and flip over to the next page. And I'm going to keep my page up so that I can copy my notes down. So you can go back and forth between the 2 of them, but for our step 3, we had that omega was 4.71 radians per second. We had that r was 0.0200 radians, meters. We know that delta x is 0.100 meters. And we did not know what delta t was, and we did not know what omega was. All right, so now I see that I need 2 equations for each of these unknowns. Well, we said in step 2 we were going to convert our delta x into our delta theta. And so in order, you think about the wheel rolling, and if I've got just a little blob of paint on it, so it leaves a paint line as it draws. As it rotates, it's going to draw that paint line, and I want that paint line to be 10 centimeters long. So how many times does it have to turn? Well, you could count circumference with that, couldn't you? But the easier way to do it is simply to use the equation that we derived. So I know that delta x is equal to delta theta times r. So that will give me my delta theta. And now I want to use my rotational kinematics. Now I have an angular velocity, and I've got an angular displacement, and I want a time. Which one of these is going to work for me? Now let's try this one. So if I have my, whoops, that goes away. Let's suppose that my theta final is equal to my theta initial plus my initial, and remember that's not going to change, times t, that's going to be my delta t here, plus 1/2 alpha t squared. Right? Now, is there an angular acceleration in this problem? No, your robot's traveling at a constant velocity, therefore the wheel must be rotating at a constant angular velocity, so that one's 0. This delta f minus delta I, or delta O I think we've been using, that's equal to my delta theta. And so delta theta is just going to be this. Alternatively, you could say, oh, well, I'm just going to start my theta from 0. And then I know that I need to turn through whatever I calculated there. Either one works, get you in exactly the same place. All right, so let's do the work. This is delta theta times r. I want delta theta in this time, So delta x over r equals delta theta. And so that equals 0.100 meters divided by 0.0200 meters. Pick up your calculator. And so we get 0.1 divided by 0.02, and that is simply equal to 5 radians. Remember our units, we want everything to be in radians for this. Okay, so now I'm going to go to my rotational kinematics, and I know that I have this is equal to that. And I'm solving for t. So I've got delta theta, which we just found, is equal to omega 0, which is right here, divided times t. So time then must equal delta theta over omega 0. So it's going to be 5 radians divided by 4.71 radians per second. You see why I need both of those in radians. So now when I flip, my radians are going to cancel. I'm going to be left with seconds. So let's put that in our calculator. So 5 divided by 4.71, and we get 1.06 seconds. So this is an important thing. If you're trying to control your robot and you don't necessarily have a distance sensor, or at least maybe not one pointed in the direction you want to go, and you're saying, okay, I need to go 10 centimeters. If I know the radius of my wheel, and hopefully you do, and then you can say, okay, if I run my motors at 4.71 radians per second, then I know that my code needs to turn on the motors for 1.06 seconds and then turn them off. And then I will have moved 10 centimeters. So this is a very common problem to solve in robotics with rotational kinematics. So up to this point, we've just been saying, oh, okay, well, my robot is here and I've got some sort of distance sensor on it, so that I could figure out I needed a barrier here so that I could see how my distance was changing. And so I could just say, okay, if this is my initial distance, when I get to my final distance, this separation should be 10 centimeters. And I could do that. What if I don't have a barrier though? Now I don't have any way of measuring my distance, even if I have a distance sensor. So I need to do it based on how fast my wheels are rotating. And if you need to get there sooner, then you simply increase the angular velocity of your wheels, and you can control the power of the motor to determine what it is. Or maybe you've got maybe you're designing your robot to have a different radius, one that's got bigger tires. You're going to cover a greater amount of distance in the same amount of time. All right. All these things are design considerations that you're going to make anytime that you're designing a system. All right, so now we've seen how we can apply this rotational kinematics into a real-world problem, launching a rock with a sling, or determining how long your motors need to run to propel your robot. In practice, you can't avoid rotational motion. Everything rotates. Very few things actually move in a straight line. So you've got to be able to control what that tangential velocity is as we go along our path. This that we've done today sets you up for being able to solve that problem. We'll see you next time.